Hey, welcome! Today, we're going on a bit of a journey, climbing what I like to call the ladder of mathematics. We're going to start with the math we all know, stuff you'd see in any school, and then see how it logically leads, step by step, to some seriously powerful ideas. So, let's take a look at the bottom and the top of this ladder, side by side.
Okay, so check this out. On the left, you've got something straight out of a school exam, right? 120 minus 89. We've all been there. It's simple, it's familiar. But then you look to the right. And what is that? That's the product rule from calculus. It looks like a completely different language, doesn't it? Almost like a secret code.
So, this is the big question for today. How in the world do you get from the simple sum to that complicated formula? And maybe even more importantly, why would you even want to? See, this isn't just about making things harder for no reason. There's a real, logical path that connects these two worlds, a path that was built because we needed it. And today, we're going to walk that path together.
So, here's our game plan. We'll start with our basic toolkit, the stuff we all know. Then, we'll hit a problem, a question of change that our toolkit can't solve. That'll force us to learn a new language, the language of curves. We'll pick up some new tools, put them to the test on a real-world problem. And finally, we'll look up and see that this ladder, well, it just keeps on going.
All right, first stop, our basic math toolkit. This is our foundation, the solid ground we're all starting from. Think of it as everything you'd find on that standard school exam.
So what's in here? Well, you've got your arithmetic, your algebra, graphing straight lines, measuring things, handling data with charts, and even a bit of probability. And you know what? These tools are absolutely fantastic for describing a world that's predictable, a world that plays by simple straight-line rules. But what happens when it doesn't?
And that's the thing, isn't it? What happens when things aren't so simple? When the world isn't a perfect straight line? This is the exact moment where our trusty toolkit starts to feel a little limited. It's time to ask a new kind of question.
Think back to that graphing problem from our toolkit. Draw the line y equals 4x minus 1. The key word there is line. It's straight. That means its steepness, what we call its rate of change, is always the same. It never changes. No matter where you are on that line, it's got the exact same slope. Super easy to measure, super predictable.
But let's be real. The world is full of curves. Things like population growth, the speed of a car, the value of an investment, they almost never move in perfectly straight lines. So, here's the million-dollar question. How do you measure the steepness of a curve? I mean, if it's constantly changing, how do you pin down its rate of change at one specific single instant? And yeah, our basic toolkit, it just can't do it. It hits a wall.
So to answer that question, we need something new. We need a whole new language, a set of tools designed from the ground up to deal with curves and change. And that brings us to differentiation. This is the heart and soul of calculus.
Let's look at one of the coolest tools in this new language. Now, don't get hung up on the crazy notation, just focus on what it does. The second derivative asks a really simple but profound question. How is the steepness itself changing? Is the curve getting steeper and steeper, or is it starting to flatten out? Just by asking that one question, this tool can tell us the fundamental shape of any curve.
It's actually pretty straightforward. If the second derivative is positive, it means the steepness is increasing, which creates a shape like a bowl opening upwards. We call that concave. If it's negative, the steepness is decreasing, making a shape like a dome. And just like that, we have a precise, mathematical way to talk about shape. Pretty neat, right?
Okay, but not all curves are simple. Sometimes they're built by mashing other functions together, like multiplying them or nesting one inside another. For these more complex situations, we don't have to start from scratch. We just need a couple of reliable recipes.
Remember that scary formula from the beginning, the product rule? It turns out it's not a scary monster. It's just a recipe. If you've got two functions being multiplied, all you do is identify them, find the rate of change for each one on its own, and then plug all the pieces into the formula. It's a foolproof method that just works every single time.
And then there's the chain rule. This is your go-to recipe for when you have a function tucked inside another one. The easiest way to think about it is like this. You handle the outside function first, then you handle the inside function, and then you just multiply them together. It's brilliant. It turns one big, complicated problem into two small, easy ones.
So we have these powerful new tools, but what are they actually good for? Talk is cheap, right? Let's put them to work and see how we can use them to figure out just how fast something is growing.
Okay, here's a classic problem that our basic toolkit would have absolutely no idea how to solve. Imagine a circular puddle is spreading out after some rain. We know how fast its radius is growing, let's say 8 centimeters per hour. That's a nice simple speed.
But think about it. The area of the puddle isn't growing at a simple constant rate. As the puddle gets bigger, that same 8 centimeters of new radius adds way more area. So how fast is the area really growing at any given moment?
Let's organize our thoughts and lay out all the puzzle pieces. First, what do we know for sure? We're given that the radius is changing over time at a rate of 8. We also know a formula from basic geometry, the area of a circle. And, using our new calculus tools, we can find its derivative, which tells us how the area changes in relation to the radius. The only thing we're missing is how to connect all of this to the passage of time.
And this is where the magic happens. The chain rule is the key that unlocks the whole thing. It builds the bridge we need. It tells us that the rate of change of the area over time is simply the rate of change of the area with respect to the radius multiplied by the rate of change of the radius with respect to time. See? It just connects everything perfectly.
And when we plug in our numbers, we get our answer. The area is increasing at a rate of 16 pi times the radius every hour. Now pause for a second and look at that. This is the really cool part. The answer isn't a single flat number. The rate of change depends on the radius. That means when the puddle is small, its area grows slowly. But when it's big, it grows incredibly fast. Calculus gives us an answer that's alive, an answer that captures this dynamic, changing reality.
Wow. We've climbed all the way from a simple subtraction problem to solving for dynamic, changing growth rates. That is a huge leap up the ladder. So, what's at the top?
Well, here's the thing. There is no top. This ladder just keeps going. And every new tool, every new level we reach follows the same pattern we just saw. It might look more complex on the surface, but its real job, its true essence, is to make complicated things simple enough for us to understand and solve. We invent new math to answer the questions the old math couldn't.
So, you see, every single step up this ladder isn't just about memorizing a new formula. It's about earning the power to ask and answer a whole new class of questions about the world all around us. From the shape of a simple curve to the growth of a puddle, math gives us the language to describe it. So the only question left really is for you. What will you ask next?